In the wood-paneled chapel of the Catholic University of Louvain in Belgium, a priest lights a candle and kneels before the statue of Christ for his daily devotion. His name is Georges Lemaitre, and it is 1927. As he rises, his eyes wander to the towering windows that line the chapel's walls, and to the stars twinkling in the early evening light. He smiles in distant reflection, imagining the sequence of events that brought that starlight to the Belgian sky. But despite his faith, Lemaitre's beliefs were lacking a creator so fundamental to the Catholic doctrine. He had no need for divine intervention when it came to the making of the universe. No seven-day miracle. Instead, he saw it as a natural consequence of natural laws and processes proved by mathematics and visible in the movements of the heavens themselves. His extraordinary insight would earn him 2 Nobel Prize nominations. For Georges Lemaitre was more than just a Catholic priest. He was also a theoretical physicist, a cosmologist fascinated with the workings of the universe. For Lemaitre, there was no conflict between his faith and his science. He saw physics as a divine path, a way to glimpse the mathematical elegance of creation itself. It was here at the Catholic University of Louvain that he began to challenge the scientific consensus of his day. At the time, the prevailing view, championed by Albert Einstein himself, was that the universe was static and eternal. But Lemaitre, poring over Einstein's own equations of general relativity, found they told a different story. They suggested a dynamic, evolving cosmos, one where the very fabric of space was expanding. This wasn't just theory. Observations from astronomers like Edwin Hubble showed distant galaxies rushing away from us, their light stretched into longer, redder wavelengths. If the universe is expanding, he reasoned, then in the past, it must have been smaller, denser, and hotter. The mathematics had laid out a history of the universe, and now, Lemaitre traced it backwards in his mind's eye. He rewinds past the dawn of humanity, past the age of dinosaurs, to a time when our planet was a molten, inhospitable sphere, slowly cooling as it coalesced from the primordial solar nebula around the glowing sun. Before that, the sun itself ignited in a blaze of nuclear glory. Gravity, the master sculptor of the cosmos, crushed a vast cloud of gas and dust into being, squeezing its core until fusion ignited. And that primordial cloud? It was the recycled consequence of many generations of massive stars living and dying before our own. These cosmic ancestors forged heavy elements in their fiery hearts, then exploded in terrific supernovae, spreading their elemental waste products across the cosmos, the very stardust from which we are made. He imagined a time before these many lineages of stars, before the chemical complexity that we enjoy, when only hydrogen and helium floated inert in a lightless universe. If space is expanding now, then in the reverse chronology of Lemaitre's mind, it is contracting. There would be a point in this dark, gassy cosmos before the first star when all the matter in the universe was compressed into a vastly smaller space. Atoms would become packed so tightly that even photons are unable to pass through. When the contracting reversed universe crushes down even further, the atoms themselves are crushed first into subatomic particles and then into pure energy. In this small, dense universe there is only radiation. Here, even Lemaitre's imagination begins to falter. The universe can become even smaller, even hotter, but what happens then? Lemaitre pushes the unanswerable from his mind, content in having grasped 13 billion or so years of cosmological history, and unperturbed by the mysteries contained within the first fraction of a second. Before Lemaitre, studies of the cosmos had largely focused on our own place within it. The 13th century philosopher Siger of Brabant was alone in venturing the statement that the universe was eternal with no beginning. This idea of a static, timeless cosmos became scientific orthodoxy. It took a unique mind, Georges Lemaitre, both a priest and a physicist, to propose a radical alternative, a universe that began at a single point in time. One respected but controversial astronomer, Fred Hoyle, railed against Lemaitre's expanding universe history. A supporter of the rival steady-state theory, which held the universe was eternal, Hoyle found the idea of a singular creation event philosophically repugnant. During a radio broadcast, he even coined the term Big Bang as an insult, a name that would ironically stick. Lemaitre's mathematics were supported by real observations of the real universe made by eminent astronomer Edwin Hubble. From the Mount Wilson Observatory northeast of Los Angeles, Hubble had gazed tirelessly through the largest aperture telescope of the time, peering at some of the dimmest parts of the night sky. He was meticulously measuring the light from distant galaxies to determine their motion. He used a principle we experience daily. Just as an emergency vehicle sounding a siren will sound different when it's moving towards us or away from us, so too the light from a star will be altered by its motion. The light waves emitted by stars moving away from us are stretched out. In the visible spectrum, the longer wavelengths of light are colored red to our eyes. And so receding stars appear more red than they actually are. This redshift became Hubble's cosmic yardstick. Hubble saw that the more distant galaxies receded much more quickly than those close by. This clear relationship, now known as Hubble's law, could only be possible if the whole of space was expanding, carrying the galaxies along with it like raisins in a rising loaf of bread. Lemaitre's theory now had powerful observational evidence. The final, definitive proof came decades later, almost by accident. In 1964, researchers at Bell Labs in Holmdel, New Jersey, were using a gigantic horn antenna to tune into radio waves bounced off some of the earlier satellites. They were plagued by a persistent background hiss they couldn't eliminate, a noise that came from every direction. Despite their best efforts, their results were plagued with a persistent noise they couldn't eliminate. At first they thought it could have been the results of pigeons roosting in the shelter of the huge antenna. Eventually, it became clear that the noise wasn't pigeons or people. It was coming from outside our galaxy. It was a property of the universe which we now recognize as cosmic microwave background radiation. This radiation is a remnant of a time when the universe was very small and very, very hot, as predicted by Lemaitre's calculations. The expansion of space has since spread that radiation out, stretching the once intense heat waves into microwaves, with a background temperature of just 3 degrees above absolute zero. Models of an expanding universe were originally based upon Albert Einstein's theories of general relativity, but when Einstein heard about this radical new theory, he was uncomfortable. Lemaitre extrapolated the universe back to what he describes as the primeval atom, which contained within it the potential for the entire immeasurable universe. One theory that reigned for a long time is that the cosmos began as a gravitational singularity, a single one-dimensional point from which all of time and space were birthed. This is not dissimilar to the singularity at the center of black holes, like the one that lurks at the center of our galaxy. If at the moment of its beginning the cosmos had been an arbitrarily dense and hot point, then the universe that resulted would have looked very different from the one in which we find ourselves. But there is another option. It may have all begun with a period known as inflation. During this inflationary period, space expanded exponentially, doubling in size from one moment to the next. In 1981, in the shadow of St. Peter's Basilica, top cosmologists gathered for a conference organized by the Pontifical Academy of Sciences. It was a fitting location. Decades earlier, the Belgian priest and physicist Georges Lemaitre first proposed that the universe began from a single primeval atom, laying the groundwork for what we now call the Big Bang Theory. Among the honored guests was a 39-year-old Stephen Hawking. Already a titan in the field, he was there to present his latest thinking on the beginning of the universe, a concept that had fascinated scientists for generations. He proposed that the universe is finite, yet it has no boundary. To explain, he used a powerful analogy: the surface of the Earth. As you travel to the South Pole, you reach a point where the concept of south ends. It's not a wall, but a point where the rules of direction simply change. Hawking argued that time itself behaves this way at the universe's origin. As you go back to the beginning, space and time curve and close off smoothly. So, asking what came before the Big Bang is like asking what is south of the South Pole. The question is meaningless because before ceases to exist. But Hawking's proposal is not the only idea venturing beyond the Big Bang. Another popular theory is the Big Bounce, which imagines our universe as part of an eternal cycle, endlessly transitioning between an expanding state and a contracting one, a cosmic dance of death and rebirth. And in the mind-bending realm of superstring theory, space-time is described by 11 dimensions. Our universe could be a mere membrane or brain floating in a vast, higher-dimensional reality called hyperspace, perhaps one of many universes in a cosmic ocean. Our understanding of the cosmos relies like a house of cards on our understanding of physics and mathematics, which continues to change and evolve. The true nature of the Big Bang and the meaning of the universe as a whole may always be incomprehensible to our monkey brains. We can only keep asking and trying to see through the fog. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think, and we'll see you next time.